ICFO in the group of Antonio Asin. And okay, stage is yours.
Okay. I hope you can see my screen.
Yes.
Okay. Good afternoon, everyone, again. Thanks a lot for the invitation. What I want to discuss today is based on these two archive preprints, which are these two protocols, classical shadows and quantum tomography, adapted for non-IID sources. Okay, so I'm going to start by giving you the main results of my work right away, which is that dropping the IID assumption in classical shadows and quantum tomography doesn't make the sample complexity worse. So we have a non-IID source that produces an arbitrary sequence of states, and we have the average state of this source. Then for quantum state tomography, we can reconstruct this time average state with precision epsilon in trace distance using this number of shots. And actually, this dependency is optimal. This is the best you can get even in the IID setting. Second, for classical shadows, if we want to estimate the expectation value of observables on this average state, we achieve the same sample complexity as the IID cases. So the number of shots depends on the shadow norm, the error epsilon, and the number of observables. Okay, so the rest of this talk would be about justifying these two statements. The two protocols we are talking about extract information from a quantum system. And the way we are doing this is by asking a source to prepare many quantum states sequentially, perform some well-characterized measurements on each one of the individual states, and process the outcomes, the classical data that we get from the experiment, to estimate some function of the states the source is preparing. Okay, a simplification most of the characterization or tomography methods do is that all the states we are preparing are independent and identical copies of a quantum state rule. So each time we ask the source to prepare or to produce a quantum state, the source gives us exactly the same state, and these states are uncorrelated to all other states and to the environment. Okay, this is an approximation, right? But this is an approximation that simplifies the math, because since we are measuring each state independently, the measurements that we get here, the outcomes, are independent random variables, which means that we can take this output, these outcomes, and use standard concentration inequalities to bound our estimation errors. You can use Hopkins inequality or Bernstein's inequality or whatever. Okay. However, real experiments usually don't satisfy this IID assumption, right? And these states might be different, and they might also be correlated among each other. For example, devices can experience parameter drift, right? Due to thermal fluctuations or calibration errors. So if the experiment is too long, the state that you are preparing at the end of the experiment might be very different from the state that you are preparing at the beginning. There are also experiments that use feedback and also mid-circuit measurements. And in this case, the state prepare at time t is by construction, depending on the previous states, right? when we have states in quantum memories, the states might share some entanglement, and also in experiments, not all states degrade at the same speed in the quantum memory, right? So for sure, the states in a quantum memory are not equal among each other. And finally, there might be more adversarial scenarios, like in QKD, for example, where someone could be adapting the preparation depending on the entire history of the experiment. Okay, so because of all these effects, and there are many references that talk about this, there is usually no a single static state being prepared, and this means that we have to change the target in our learning or tomography method. And one operationally meaningful quantity in an experiment like this is the time average state, this one that we see here, which represents the effective trajectory of the device over n rounds. Yeah, the problem here is that once we drop this IID assumption to target this average, the standard concentration inequalities that we use to prove things break down, because these outcomes are no longer independent, right? So we have to adapt the math to tackle this problem, the non-IID problem. Okay, so before we do calculations, we have to formalize this non-IID behavior. So we assume there is an adversary or there is an environment which controls the preparation of my quantum state. Since the adversary is preparing n quantum states and I measure n times, the experiment is divided in time steps from 1 to n. At each one of these steps, information is being produced. So there is information about the outcomes, about the settings chosen. That is something that I know because I assume my measurements are perfect. But there is also information that I might not know, like the temperature or the memory of the environment, for example. And the way we represent this information is by defining these objects, f of t. So f of t represents the entire of our experiment up to step t. Yeah, in our scenario, we assume the adversary is very powerful. So he or she knows all the information at each step, like the outcomes we get, the temperature, the memory of the environment, and so on. So the adversary knows these variables, or yeah, in this case, they are going to be sets f of t. Yeah, and also we assume that each round, the state that is presented for measurement is fixed based on this history. So the adversary can use all the past to prepare these states, and then at step t, I have a particle of some fixed dimension in some unknown quantum state, and I measure this particle with my perfect trust measurements. Yeah, this model also includes the case when we are measuring a globally entangled state. So imagine we have n particles, and we perform sequential local measurements on each one of these particles. So for the first particle, when we measure it, since we are only acting on this particle, the statistics is going to come from the reduced density matrix of the first system. So this will be rho 1. Then after the first measurement, the states, they get updated, right? So depending on the outcome k of the first measurement, the second state will be a different state of this one. And yeah, this is a state conditional on the outcome of the first measurement. So for sure, these two states are not independent. And then you do the same for each one of the rounds. So for each one of the rounds, you will have a quantum state that depends on the previous measurement outcomes. So this is the model we use for non-IID protocols when we have entanglement, and it's something that they use in this paper too, where they do self-testing of quantum states without assuming IID. Something I think it's important to emphasize is that here we are not estimating properties of reduced density matrices. We are estimating properties of trajectories. So if we start with this state, for example, in round one, the statistics is going to come from this state, right? However, if we measure this PVM, the outcome is going to choose one of these two states. And then in the second round, the statistics is going to come from this state or this other state, and this is different from estimating properties of the reduced density matrices, right? Because with reduced density matrices, we would have the identity in both cases.
Sorry, can I ask you a quick question?
Yeah, please ask questions. All questions.
So to understand, so the idea here is to use, so you're using estimators that depend on the full trajectory. Is that what you're saying? Instead of using single shot estimator,
yes,
you're gonna somehow, I guess, define a function of the entire sequence K1, K2, etc. Right? That,
yes.
Okay.
Yes. Yeah, thanks for the question. Ask more question, because since I don't see you, I feel I'm talking alone. But yeah. So how do we estimate things in this non-IID?
Can I ask a question before going on about the last slide? When you made the example of the entangled state, okay? The non-IID hypothesis is on different copies of the entangled state, right? I mean, if I prepare different copies of rho n, and these are not IID, right? This is the right interpretation, or?
Yeah. What I'm trying to say is that, so imagine you have an adversary, and this adversary has a huge entangled state, and this adversary is feeding you with copies, not with particles of this entangled state.
Okay.
So this is what I'm trying to see. For example, yeah, if an adversary has a G8Z state, and he is feeding me copies, not copies of the G8Z state. He's feeding me with the particles with this state. When I measure the state of the next particle, he's giving me changes, right?
Yes. Okay.
Because this adversary will know the outcome of my measurements.
Thanks.
But
yeah,
well, I ask another one. So at the beginning, you said the problem statement is you want to kind of estimate properties of time average states. At some point, you said that, right? You have the sum over T of rho T, right? But this slide seems more general than that. Like from this slide, I would say you might also want to estimate, I don't know, an entanglement weakness of a bunch of large entangled state, right?
You can also do this. Yes. So actually, this framework
is a special case.
Yes. Yeah, actually, this framework is general, and then we are going to restrict to these shadows and quantum state tomography, but you can use it for fidelity estimation if you want to measure weaknesses, and yeah, it's more general. Yeah. Okay. So something problematic here is that the state changes at each point in time, right? Then we only see each one of the states in the sequence once. So we measure it, we get one click, and then the state is gone forever. So we have to be careful the way we extract information about the system. And for our problem, we are going to use single shot estimators. So to construct a single shot estimator for the states, we perform an informationally complete measurement that is well characterized, and we construct our estimator as a function of the outcomes. So for each outcome k, there is a matrix rho k that will be an approximation of this quantum state, or an estimation. Yes, an estimation of this quantum state. The crucial property here is that this estimator is unbiased, and this means that if you take the expectation value of the estimator over the measurement probabilities, the probability of each one of the outcomes, it exactly equals the true underlying state rho. Okay, so this is quite general. You can do it for many types of measurements. And if we measure PUVMs that are two designs, like SIG PUVMs, for example, what we get are single shot estimators of this form. So this is the form these matrices are going to have. And if we measure random Paulis, we get single shot estimators of this other form. Now, obviously, this single shot matrix is going to be a terrible approximation of the actual state. It has a huge variance because it comes from only one photon or one qubit measurement, even a positive matrix. So in the IID setting, what you can do to improve the quality is add many of these matrices. And if we add sufficient matrices, we have convergence to the state rho. And yeah, to actually prove this, to actually prove the convergence, and have the actual number of shots or single shot estimators you need, people use a concentration inequality, matrix variance inequality, and we get results like this. That is for quantum state tomography, and says that if you measure this number of shots, the sample average is going to be close to the true average in one norm for the IID case. Okay, now coming back to the non-IID setting, the adversary can choose the state rho t, but the assumption is that
Leonardo, the D-cube scaling is optimal to your knowledge, or?
Yes, this is optimal. Actually, it's B times the rank squared.
Okay.
That is the best you can do. Yeah. Thanks. Yeah, you can find lower bounds using information theoretical inequalities like Fanos, Lehman. Yeah. So. Okay, so yes, the adversary can choose the state, but they cannot. Well, the assumption we make is that our measurements are perfect. So the device, once, or the adversary, once the particle enters our measurement device, the adversary cannot control the randomness of the measurement beyond Born's rule. So the outcome probabilities depend on the previous history, but only through the quantum state. So we have these. Okay, so because of this, the single shot estimator we have is conditionally unbiased. We call this conditionally unbiased. So if we calculate the conditional expectation, the expectation of the single shot estimator given all the previous history, the dependency on the history of these probabilities only enters through the quantum state, right? And then, as we saw on the previous slide, from this average, we get the true quantum state. So even if the state was chosen based on the past, the specific, like the conditional expectation gives us exactly the state prepared at that round. Okay, if we define our estimation error as our single shot matrix minus the true state, the expected error conditional on the past is exactly 0. So this means that if there is some adversary preparing the state, but our measurements are perfect, they cannot bias my expected error. And this is something that is key for the rest of the presentation. Yeah, the adversary cannot bias the expected error, even if he knows all the previous history of the experiment.
Sorry, can I ask, so what do you mean exactly by adversary here? So the idea is someone that prepares this state in a way that might make you maximize the estimation error or something? In what way is this an adversary?
No. Yes. Yeah, we will see that even if the adversary, yeah. What I want to say here is that an adversary, someone, or the environment, who is preparing the state, depending on all the information this person could have, this error, if you use these single shot estimators, like that we were talking about, they cannot bias the error. So in average, the error will be 0.
Like, why should it bias the error? Maybe I don't fully understand what you mean by adversary here.
Because they cannot predict the future. So this is a bit like a random walk, this property, in the sense that these errors behave a bit like a random walk. So in a random walk, the position at some step depends on the previous step, but the expected increments. So if I am in position X, in average, in the next step, I will be in the same position. And this is saying the same. If I cannot predict the Born rule or the result of the next measurement, I won't be able to design a state that is able to bias the error of the estimation in average.
But how would biasing the error work here? Like you're saying, the adversary wants to prepare a state in such a way that you can't reconstruct that state. Like, because if the task is reconstructing the state at every step, rho t. But even if the state rho t is different, I mean, I just measure rho t and get an estimate of that state, no?
Exactly. So that is the property. That is the nice thing about these single shot estimators. If you try to use a different estimator, maybe an estimator that takes information from several rounds, there the adversary could maybe bias the estimation. But this in this case, he or she cannot do it exactly, because if the adversary changes the state, I'm going to estimate that state, right?
Right. So that adversary could like change the state from time to time, and if you don't know it, that's what you're saying. And then if you don't know that the state changed between one shot and the other, you would be estimating different things and get a error.
Yes. Okay. So if the adversary changes the state, then my estimator is like, I'm going to still be able to estimate that he changed the state. Well, not this. In that round, that the adversary changed the state, my estimator will be an unbiased estimator of that changed state.
Okay. Right.
Yeah. I don't know if it's clear.
Yeah, I think it makes sense.
Okay. Yeah. So this property, in probability theory, this property, this sequence of errors is called a martingale difference sequence. So it has a name. Okay, so we saw that the single shot estimators can be correlated between rounds, but they are conditionally unbiased. So the errors in average are 0. And this is the property we need to replace the standard concentration inequalities with non-IID concentrations inequalities. And what we use here is Friedman's inequality. And you can think about it as Bernstein's inequality, if you know it, but designed for martingales, for random variables that satisfy this the property we were talking about. Okay, so this is a scalar version. So we have a set of random variables, which in our case will represent our estimation errors. We need them to be bounded by some constant R, and they have to be conditionally centered. So the conditional expectation needs to be 0. Then they also have to satisfy this condition. That is some sort of conditional variance. So this is called predictable quadratic variation. And yeah, you can think about it as just the variance of the process. And then we have this. We get an exponential tail bound that looks exactly like a standard IID bound. Like just replacing these averages and variances by these new quantities. So this says that if we sum all these terms, if we sum all the errors, the probability of this sum being large will be small. Okay, so this was for numbers. For random matrices, that is what we use in quantum state tomography. Our estimators are not numbers, they are Hermitian matrices. And in this case, we asked these matrices to have a bounded norm, to have 0 conditional expectation, and that the norm of this sort of variance is some finite number. And then we have the same concentration, basically saying that the sum of these matrices is not so large in probability. Okay, yes. So now we have the mathematical tools, and we actually want to use to prove things in the non-IID regime. So let's start with quantum state tomography. That is easier. So we are going to focus on projected least squares quantum state tomography. So this is maybe the simplest method of doing tomography, but it's quite effective, and actually it's optimal in sample complexity. All right, so in this protocol we have 4 steps. First, we have the data collection. We have a source that prepares a quantum state and sends it to a measurement device that implements some measurements on POVM that we know. And we repeat this measurement procedure n times, and we record the outcomes. Then we construct the single shot estimators. So for every single outcome, we map it to its corresponding single shot matrix, the single shot estimators that we just saw. And this is the matrix that we proved it was conditionally unbiased, right? So even if the adversary is changing the state, we are still estimating it. Then we compute this empirical average. So this is just adding these n single shot matrices together and then divided by n. And this is also an unbiased estimator of the quantum state. And then yeah, some problem here that we can have here is that we are using a finite number of shots, right? So this matrix has statistical noise, and it can have negative eigenvalues, meaning that there is not a quantum state, right? It's not physical. So the final step we do here is the projection. We take this noisy matrix and we project it into the space of valid density matrices. So what we do here is we find the physical state that is closest to our empirical average. And now the idea is proving that this protocol works also for the non-IID regime, but this time estimating the average state of the experiment.
Sorry, this is less of a shadow tomography setting, right? Like in a shadow setting, you instead of trace distance, you just want to ensure that like projections, like the estimators for many observables are accurate. So the physical projection bit, you don't need it in that context, right?
Sure. Yes. Yeah, they are quite similar. So first, I think there is a paper, this paper in 2020. And in this paper, they prove this convergence to the quantum state. They propose this projected least squared quantum tomography. And then in the classical shadows, they use very similar techniques to prove things in the classical shadows paper. Actually, Rich, who is one of the authors of the classical shadows, is also in this paper.
Okay.
Yeah. But yeah, the estimators you use are the same. So okay, so we have Friedman's inequality, we have the single shot estimators, and we know that these single shot estimators satisfy this property. So to use this inequality to prove convergence, we have to bound two things. We have to bound these, and we have to bound these variance. As an example, if you have this single shot estimator, that is the one you get when your measurements form two designs. Yeah, this estimator is conditionally unbiased. So conditional on the past, the expectation is 0. Then if you calculate the spectral norm of this operator, you find that is bounded by the dimension d, because you have this d plus 1 factor in front. And the calculation of the variance is a bit more complicated, because in principle, the probabilities are functions of the previous history. And also you have the square of this single shot estimator here. But since the state is fixed, when you measure, we recover the usual Born's rule, and then everything becomes standard. So these are calculations that are in this paper. And then we get this bound for the predictable variance. Then you plug in these bounds onto this inequality, and we get this. So this is a guarantee that our empirical average is close to the true time average state in spectral norm. So yeah, something we see here is that if we want a small error with high probability, we need a number of shots proportional to the dimension, right? Because we have this n on top and the dimension in the denominator, and we want this exponent to be as large as possible. Yeah, so this is the demonstration, but basically, I think the most important part here is that this is exact same scaling that you get in the IID case. So if we want to estimate the average density matrices, we just use the same protocol with the same number of shots, and we are going to have the same error. Do you have any questions here?
Maybe just a clarification. So you're literally just using the single shot estimators at every single step, right? You said. So you're not processing all the data together here. So
No.
The usual technique also works to estimate the average of the states. Okay.
Yes, and actually the demonstrations are quite similar. Is basically the same demonstration. So if you matrix versus inequality is the same here, but here you have averages instead of conditional averages. So yeah, so it's like a generalization of the other demonstration, but and that is why you get exactly the same constants, because this inequality is the same, but for martingales. Okay, so we've seen how to reconstruct the full quantum state using tomography, but full tomography is too expensive for large systems, right? The sample complexity is exponential in the dimension, and often you just want to predict specific properties like the magnetization of a system or the value of an entanglement weakness, and for this it's better to use the shadows formalism. So in the ideal setting, we repeat our experiment n times. So in each round, we prepare our state rho. We apply some random unitary that is usually a global Clifford circuit or a local Pauli measurement or a local Pauli rotation, and we then measure in the computational basis to get some outcome, just as we did in tomography. We take this classical outcome and map it back to a single shot estimator, to a matrix, which is going to be our shadow. So depending on whether we use random Clifford circuits or local Pauli measurements, we get these specific formulas. We get different types of shadows. Again, these shadows are unbiased estimators of the quantum state, but they are not physical states. So now, instead of adding all these matrices together to build a density matrix, we compute the property we care about immediately. So for any observable O, we compute the trace of O with our single shot shadow, and this gives us a single shot number that is going to be an unbiased estimate of our true expectation value. Yeah, but here there is a problem, and the problem is that the single shot estimator is very noisy, right? Because we are using only one shot, and also because this quantity has a heavy tail distribution, meaning that it can produce very, very large outliers. So if we just take a simple average over the n shots, a single outlier could completely destroy the average, destroy our estimation. So in the standard classical shadow protocols, they use a technique called the median of means. So we take our n shots, our n estimates, and we split them into k batches of equal size. First, we compute the standard average or the mean, right, within each batch, and then we take the median of all these k-means. Then if we have one outlier inside these means, the median will see it, right? And then this will give us a highly robust final estimate. Okay, this is something that works very well. It works perfectly for IID settings, because the median of means needs this IID assumption. But if the states are correlated in time, or we have an adversary, this adversary could put just one outlier in each one of these batches, and then all these means would be would be biased. The median wouldn't be able to solve this problem.
Can I ask you something? Even in the IID case, for the have you found an actual case in which this median of means is really necessary? Because it seems to me that even like as long as you have bounded observables, which is usually bounded estimators, which is usually the case, no, when observables are bounded, you still have the usual guarantees without using median of means. Like IID works for any bounded estimator.
Yes, but you see this at some point you have to calculate the bound for this quantity here for the shadow, and then you get this d+1 factor in front.
They're saying and then, even if they're bounded, the actual bounds might depend on dimension, because you do it on the O, right? Not on row.
Yes. So that is why they need this median of means. Yes. Well, yeah. In practice, the probability of having one of these outliers is very, very low. It's like 10 to the minus 20 or 10 to the minus 30. So in practice, it never happens. But yeah, if you want to make a proof, you have to.
I mean, standard proofs.
Yeah, you cannot prove it, right?
You still have the guarantees usually. I don't know, when we try this stuff, I never actually saw an advantage using median of means over just some normal mean, despite what they. I mean, I know the original paper they used median of means, I remember, but never actually saw a difference, an advantage in using it.
In the math or numerics or.
I mean, both. Even the math doesn't need it if you just want the scaling without d, log m, log 1 over delta. Those just use IID, so they just assume that that the estimators are bounded. Now you can argue that the bounds might depend on d, and so therefore the guarantees work, but with different coefficients, scaling coefficient. That is possible. In practice, I never saw different, but maybe I don't know, for very large dimensions. I don't know, maybe.
Yes.
Something.
Yes. So actually, yeah, because in my protocol, actually, I had to change this median of means. But it was because in the math, I was seeing this dimensional factor in front. So I had to change it to a truncated estimator to avoid this. So yeah, as I said, the median of means approach is built on the idea, the demonstrations are built on the idea of independent batches. But yeah, if you have non-IID noise, then the batches are not independent, and then the proof doesn't work anymore, right? So what we did in my paper is that everything is the same until the part we estimate things. So we prepare state, we apply random unitary gates, we construct shadows, and we calculate these trace. But here, instead of splitting the data into groups, we process every shot individually using a truncated mean estimator. So what we have to do is just choosing a truncation threshold. That is just a number. For now, it's just a number, but we'll see that it depends on the shadow norm. And then for every single shot estimate, we check its value. So if the value is within the threshold, we keep it. But if it's larger, we truncate it exactly at t. So we are just mapping the noisy estimates to a bounded range minus t and t. And this is something that kills the outliers, right? If you have an outlier, we just truncate to the value of t. And then we take the average of these truncated values. And this is the estimator for the expectation value of an observer. Okay, so this is the result for the modified protocol. So we have k observables, and we have the average state, and we want to calculate these quantities. And then the shadows estimators satisfy these if we choose the truncation value as this, and the number of shots is larger than this quantity here. Yes. Something important here is that this is the exact same scaling as the standard classical shadows protocol with the shadow norm on top and the logarithm of the number of observables. But this number is of the order of 5. So actually, this truncated estimator improves the constant you have in front here. So it could be even better than standard classical shadows for the IID case when you want to run real experiments, right? Because in real experiments, you care about these numbers that are here in front. Do you have any questions about this, like the modified protocol or the truncation or something? Okay. I don't know how much time we have because I have a bit of the about the demonstration, like an outline of the demonstration, but
say 10 minutes.
10 minutes. Okay, great. Okay, so actually what we want.
I think we lost you.
Okay. That's great. Maybe he can read us.
What? Were you saying something?
Yes, we lost you for 10 seconds, let's say. And also the sharing, maybe? No, the sharing is here. Okay.
Okay, now you can see and you can
yes.
hear me, I guess. Okay, so I was saying that I'm going to give an outline of the demonstration of why this protocol works. So we want to bound this thing, the estimator, minus the true value over the average state of the sequence. And yes, now we truncated the estimator, right? And this is something that adds some bias. The estimator is not unbiased anymore. And then the first step is to decompose our total error into two distinct parts, like the bias and the fluctuation. So this YT is the truncated estimator, and this is the exact quantity we want to estimate. Then we add and subtract the expectation of this quantity, the conditional expectation of the truncated estimator, and we use triangle inequality. Okay, so this is the deviation of the truncated estimation from its average, so it's some sort of location. And this is the deviation of the average of the truncated estimator from the true quantity we want to estimate. So it's a bias. And the idea is to make these two things as small as possible. Okay, so let's look at the bias first. To bound this error, we notice that these two things are the same, this and this, because the average over the shadows is equal to the true value at that round. Then using this formula that is just algebra, you get this. This is x, and this is y. And the quantity that you get in the numerator is just the definition of the shadow norm. And then, since we have the freedom of choosing the truncation parameter, choosing t to have this value and substituting here, you obtain that b is less than epsilon over phi. So the estimator is biased, but you can control the bias and make it small by choosing a good truncation parameter. Now,
sorry,
for the fluctuation,
can you go back to the slide still?
Yes, of course.
Sorry. So this norm of O is the what, shadow norm or operator norm?
This norm?
Yes.
This is the shadow norm. Yes. So
okay.
The truncation parameter depends on the shadow norm.
Because I mean, like, if there was an operator norm, the bound is kind of, I mean, the maximum value of the estimator is this norm, right? Now, okay, if it's the shadow one, I'm not sure, to be honest. Maybe it's different.
Yeah, for example, if you use Clifford shadows, I think the shadow norm is like 3 times the operator norm or something. So yes.
Right. Okay. So here you're trying to truncate at a level that is kind of compatible with more or less the maximum value of the observable, but not precisely the maximum value.
Yes. Okay. Yeah.
Because if it is very close to the maximum value, the truncation does nothing, right?
Exactly. Yes. Actually, the need of the truncation is to bound this fluctuation. So yeah, this is the fluctuation, and here we want to use Friedman's inequality. So to use Friedman's inequality, you have to bound 2 things. You have to bound the step size, and you have to bound the variance. So for the step size, you have these, and because we truncated our estimator, the maximum value of this quantity is 2t. So this is exactly why we couldn't use the standard shadows, because if we didn't truncate here, we would have a bound depending on the dimension. This would be just the like the operator norm of the shadow, and this is something that goes like the dimension. So this is why we needed this, or why I needed this truncation step. I couldn't make the proof work with the standard shadows, but yeah, maybe it's possible, but I couldn't manage without the
For what kind of observables? What kind of observables are you considering here? Like, is it completely general or specific kinds?
Yeah, no, the observables are general. Yes. Yes, but so the problem here is not the observable, because for example, for the shadow norm, the shadows that you get using random Paulis, you don't have this problem. You don't have this problem. But when you use shadows based on Clifford circuits, you have these extreme outliers. So it also depends the way you construct the shadows and the shadows you're working on.
I just the thing about outlier, if the observable is like a projection on a pure state, for example, right? The values you can take is between 0 and 1.
Yes.
So, I mean, what do you mean outlier, right? If the bound is 0, 1, outlier cannot be like very large.
Yes. I see what you mean, but in the proof of the shadows, you have you have your frame, and the shadows are your dual frame, right?
Yes.
And these elements of the dual frame are multiplying your observable. And then these dual frame elements have a factor of the dimension in front if you choose random Clifford, if you use Clifford shadows. So there is where this problem come from, I think.
The point is that the dual state, the dual are not proper states. Let's say
Yes, exactly.
So also if you compute the overlap, is not, you're not computing the overlap between 2 states, but between the states and something else. Let's say, and it's not bounded anymore.
Yes.
With the
You're completely right. Yeah. And
Right.
this something else.
The dual is p plus 1 the state. So when you project over the other thing, you get p. Okay, that makes sense. Okay, sorry. Go ahead.
Yeah, no, it's good, this discussion, like, yeah. But maybe there is another way. So, but this is the way I found to solve this, the exponential scaling. And yeah, the variance is exactly the same as the standard classical shadows. So then you have this bound for the maximum size. You have the bound for the variance. You apply Friedman inequality, and you get these. And then if you choose n large enough, this is going to be smaller than this quantity with high probability. And okay, now we have a bound for the fluctuation, a bound for the bias, and then you have this. This is satisfied if you choose this number of shots. So this is the proof, but the important thing here is that you get exactly the standard ID scaling. So with the same dependency on the shadow norm, an epsilon, but this time for the average of the sequence of states. More questions? Or maybe not, because I think I'm running out of time. So then you can do the same for quantum channels. It's exactly the same, but you have to work with the choice state of the channel. And yeah, as a summary of the presentation, what I can say is that the IID assumption is broken in real hardware. So you have memory effects, you have drift, you have adaptive noise, and other things. Then tomography and shadows and probably other estimation methods can be modified to try to target this average state. So we estimate properties of the average state of the experiment. We can do this because the sequence of estimation errors forms a martingale difference sequence. It acts a bit like a random walk. And then because the sequence of errors you have satisfies this property, we can use Friedman's inequality to show the convergence of our estimators and show that they retain the same IID sample complexity, but this time under adaptive noise. Okay, so this was my presentation. Thank you for your attention.
Thank you very much.
Thanks a lot. Thanks a lot, Leonardo. I don't know if there are other questions. This is the right moment. It's nice, this clapping hands.
Thank you.
Maybe one question. I was wondering, so at the end of the day, you're working with, so the general setting is on trajectories, but then the method you actually use doesn't leverage trajectories. So I wonder, what do you think would happen if you actually used trajectories? Could you get better performances?
Trajectories in what sense?
Well, currently you're using functions of the individual shots, and then you're just taking the average.
Yes.
Exactly like you would normal protocol. In this case, this is the same thing, just the underlying state is changing and you're kind of changing the target, right?
Yes, exactly.
But in principle, you could use functions of more than one shot together, which kind of seems natural in a context like what you're talking about, right? Because you actually, like if you had an entangled state at different times and you wanted to estimate something like that, it's kind of natural to do something like that.
Mm-hmm. Yes, actually, I didn't think about that, but actually that would be a good idea, a very good idea. Yeah, actually, I don't know what techniques I could use. So I use these because the proofs could be extended very easily from the standard IID case to this non-IID case to target this average state. But to do trajectories, I don't know what techniques I could use, but yes, even if you can do it.
Shadows, for sure, but
yes, clearly, yeah, not the standard shadows, but other things. But if you are able to estimate trajectories, that would be very interesting because you could target non-linear quantities of the